Welcome to MathAlgo Studio, where math meets code. This is Computational Geometry series, designed to take you from beginner to advanced. You will see more than 200 plus videos on this series. In the previous lecture, we studied the dot product. The dot product helped us measure alignment between vectors, and it returned a scalar value. Now the question is, what if we want a vector that is perpendicular to two given vectors? In many real-world problems, we need a vector that is perpendicular to a surface or a plane. Examples include surface normals in CAD, orientation in 3D graphics, torque in physics, and collision detection. This is where the cross product becomes essential. Now let's understand the cross product geometrically. Here we have two vectors A and B, shown in the same plane. When we take the cross product of vector A with vector B, we obtain a new vector C. This resulting vector C is perpendicular to both A and B. That's why you can see vector C pointing out of the plane formed by A and B. Mathematically, we write this as C equals A cross B. Unlike dot product, the cross product works only in 3D space. The direction of the cross product is determined by the right-hand rule. Point your index finger along vector A, your middle finger along vector B, and your thumb gives the direction of vector A cross B. An important thing to remember is that the cross product does not lie in the same plane as the original vectors. Instead, it always produces a vector normal to the plane defined by A and B. This concept is extremely important in computational geometry, especially for surface normals, orientation tests, 3D graphics, and physics simulations. Geometrically, the cross product gives a vector that is perpendicular to the two given vectors. Its magnitude represents the area of the parallelogram formed by vector A and B. Now let's look at the cross product in mathematical and geometric detail. On the left side, we have two vectors A and B forming a parallelogram. C is the cross product. The shaded region represents the area of the parallelogram formed by vectors A and B. An important fact is that the magnitude of the cross product gives exactly this area. Now let's move to the component form. If vector A is given as AX, AY, AZ, and vector B is BX, BY, BZ, then the cross product across B is computed using a determinant with unit vectors I, J, and K. Expanding this determinant gives us a new vector in 3D space. Geometrically, the magnitude of the cross product C is defined as magnitude of A into magnitude of B into sine theta. This value is a scalar, and it represents the area of the parallelogram formed by vectors A and B. In the next slide, we'll see one numerical example. Let's take an simple example. We are given two vectors. Vector A equals to 2, 1, 0. Vector B equals 1, 3, 0. Since both vectors have no z components, means both vectors lie in the xy plane. Their cross product will point along the z-axis. Now, let us calculate the cross product using the determinant method. We write the unit vectors I, J, K in the first row, the components of vector A in the second row, and vector B in the third row. After expanding the determinant, we obtain the result. The across B equals 0I minus 0J plus 5K. So, the final cross product vector is 0, 0, 5. The magnitude of the cross product is the square root of 0 squared plus 0 squared plus 5 squared, which gives us 5. Geometrically, this magnitude represents the area of the parallelogram formed by vectors A and B. We can also verify this. Find the magnitude of A and B. Using the dot product formula, we find the angle theta, that is angle between two vectors. Finally, we can get magnitude using the formula we have. We get same answer 5 in both cases. After implementing the dot product in C++ in the last lecture, we saw how it helps us measure the alignment between two vectors. Now, in this lecture, we'll move one step further. Instead of getting a scalar value, we'll learn how to compute a new vector that is perpendicular to two given vectors. Create a new function which will return the new vector, that is cross product. Create a function for magnitude of cross product. Modify vector A and B to compare results. Now run this code to see results. This is same values we get earlier. We solved manually this problem. Now let's discuss some important properties of the cross product. First, the cross product is anti-commutative. This means the order of vectors matters. If we reverse the order, the direction of the result also reverses. Mathematically, A cross B is equal to minus B cross A. Second, the cross product follows the distributive property. So, when vector A is crossed with the sum of two vectors, it distributes just like algebra. A cross B plus C equals a cross B plus A cross C. Third, we have the Jacobi property. If we take three vectors A, B, and C, and cyclically apply the cross product, the sum of these three terms always becomes 0. This property is very useful in advanced vector algebra and physics. Fourth, the zero vector property. If either of the vectors is a zero vector, then their cross product will also be 0. This is because there is no area formed. Finally, consider the cross product of perpendicular vectors. When two vectors are at 90 degrees, the sine of 90 degrees is 1. So the magnitude of the cross product becomes the product of their magnitudes, which geometrically represents the area of a rectangle. These properties help us understand both the algebraic behavior and the geometric meaning of the cross product.